Hi, in this video, we'll be looking at the types of matrices. In an earlier video, we already talked about the meaning of matrix. We looked at the order of a matrix and the element or position of elements of members in a matrix. For this video, we'll be looking at the types of matrices. Now, these types of matrices that we have, we endeavor in how, or we help us rather, in how we solve questions on matrices. So the types are actually kind of important. So once you know the type of matrix, then solving questions on matrices becomes easier. Now, the first type we want to look at will be the rectangular matrix. Rectangular matrix. And what does it mean? So this is simply a type of matrix where the order is not the same. That is, the number of rows is not equal to the number of columns. Remember, in the earlier video where we talked about the order of a matrix, we said the order of a matrix, we know the amount of rows we have, we know the amount of columns that we have. So once the number of rows is not equal to the number of columns, then such type of matrix is a rectangular matrix. A typical example, so when we have 3, 4, 5, 2, 4, 6. So this is an example of a rectangular matrix because this has 2 rows and this has 3 columns. So when the rows and the columns are not equal, another example, 3, 4, 5, 6, 7, 8. So this is also a rectangular matrix. This is a 3 by 2 type of matrix or order of matrix. So when the number of rows and columns, when they are not equal, then we say it is a rectangular matrix. All right, the second type of matrix we want to look at will be the square matrix. Square matrix. So of course, this simply if the former one or if the first one we talk about the rectangular matrix, so the number of rows and columns are not equal. For a square matrix, it means the number of rows and columns are equal. So we have example. So this is a square matrix. You can see it has 1 row, 1 column. So this is also a square matrix. 2, 4, 6, 8. You can see 2 rows, 2 columns. So this is also a square matrix. 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, this is also a square matrix. Now, what are the importance of this? When we get to finding determinant, adjoint, inverse, we come to find out that we can only find the determinant of a square matrix, not a rectangular matrix. Not to totally discard rectangular matrices because we are still going to meet a lot of them, especially when it comes to addition, subtraction, and multiplication of matrices. So that's why I'm taking time to take these types of matrices separately. So once the number of rows and columns are equal, then such type of matrix is said to be a square matrix. All right, so let's move on to other types of matrices. So moving on, we have so the next matrix we're going to be talking about will be the row matrix. Row matrix. That's number 3. Row matrix. So as the name implies, so this is a matrix that has a single row, just a single row, irrespective of the number of columns it has. Like an example, so this is a row matrix. Consider it has a single row. This is also a row matrix. 4, 5. So this is also a row matrix. So when a matrix has just a single row, so we can also classify it as a row matrix. Of course, this row matrix is a square matrix, while this row matrix is a rectangular matrix. But then, like when it has a single row, we call it, or we can call it a row matrix. So also we have the column matrix. Column matrix. So again, this is a matrix that has a single column. So another example. So this is another example. So this is a column matrix. So also we have 2, 4, 5. So this is also a column matrix. So also a column matrix. Okay, number 5, we have the zero or null matrix. Zero or null matrix. So for a zero or null matrix, so this is simply a matrix where all its members or elements are zero. So for an example, let's say this is, you can say this is the elements or the members of this matrix is zero. So this can also be a null matrix when we have something like this. So irrespective of the order. So this is a null or zero matrix. All right, so number 6, moving on to the diagonal matrices, or matrices rather, diagonal matrices. Okay, so let's just try and clear this part a bit. Okay, so number 6, so diagonal matrix. Okay, so what does a diagonal matrix, or what does it entail? So a diagonal matrix is a type of square matrix where the non or what's it called? All the non-diagonal elements are zero. I'm going to repeat myself. For a diagonal matrix, it's actually a square or a type of square matrix. We have different types of square matrix. But a diagonal matrix is actually a square matrix where all non-diagonal elements are zero. So, like an example, so let's say we have a 2 by 2 matrix, which is a square matrix, and then we're having 2, 0, 0, and 6. You can see that this is my diagonal, that non-zero, non-zero digits, but the other members, this one that is above diagonal, this below diagonal, are zero elements. So when we have a diagonal matrix, then what we're referring to is that the diagonal will be non-zero elements, while the non-diagonals will be zero elements. So another example, just to make this a bit decent. So let's say we have 2, 0, 0. So 0, 5, 0, then 0, 0. Okay, so let's write this properly. So 7. So you can see also, so you can see the diagonal, this diagonal here, diagonal non-zero elements. So the diagonal are non-zero elements, but all the other surrounding members are zero. So this is for diagonal matrix. So moving on to the seventh one. For the seventh matrix that we have, so it's also a special type of the square matrix, identity matrix. Okay, identity matrix. So for the identity matrix is actually a square matrix in which all the diagonal elements are 1 and all other elements are 0. So you can see for a diagonal matrix, we said the diagonals are non-zero elements while the others are 0. For an identity matrix, the diagonals will be equal to 1 while all the members or all the other members would be 0. So for example, let's say we have 1, 0, 0, 1. So this is a 2 by 2 identity matrix. 2 by 2 identity matrix. So let's see that of a 3 by 3. So we have 1, 0, 0. We have 0, 1, 0, and then 0, 0, 1. So this is an identity matrix. So you can see the diagonals are 1, while the other members are 0. So this is also a type of square matrix. So we have about 3 of them. So let's quickly talk about the third one. So we have the scalar matrix. Scalar matrix. So the scalar matrix is kind of identical to the identity matrix, but this time around, instead of the diagonals to be set to 1, the diagonals will be set to the same number other than 1. So it has to be uniform, unlike the diagonal matrix, where you can see this is 2, 5, and 7. For a scalar matrix, we have, so we're starting with 2, then we have to, the diagonals should be 2 all through, so 0, 0, 2. So this is a scalar matrix. So it's a type of square matrix in which all the diagonal elements are equal, but they are not equal to 1. If they are equal to 1, then we call them, or we call it an identity matrix. So the reason why we call it an identity matrix, we'll find out in the next video that we're going to be talking about the addition of matrix and the multiplication of matrices. All right. Now we also have the triangular matrices. Like we have the upper triangular matrix and then the lower triangular matrix. So we'll talk about the upper first, the upper triangular matrix. Upper triangular matrix. Okay, so for this upper triangular matrix, this is also a type of square matrix actually. So we said we have 3, but apparently we have more than 3, so not 3. So upper triangular matrix. So for upper triangular matrix, it looks like it's actually a square matrix in which all elements below the main diagonal, so all the elements that are below the main diagonal. So let's say we were to have 2, so this is my, okay, so let's just use 3 and 6 for here. So this is my diagonal. So all the elements above the main diagonals are non-zero elements. So non-zero should be 2, okay, 4 should be 6, okay, and all the elements below it are 0. So this is 0, 0. So this is our upper triangular matrix. So upper triangular matrix. So you can see that the numbers or the elements above the diagonals 2, 3, and 6 are non-zero, while the members that below the diagonals are 0 elements. So 0 elements. Now this is quite useful when you are doing the Gaussian, or when you are trying to solve a system of linear equations using the Gaussian elimination method. You want your matrix to be like this, or you want to work your matrix towards this way, and then you can now start solving your question. Okay, another type of matrix that we have, the 10th one that I want to talk about, that will be the lower triangular matrix. So for this one, that's just the inverse of what we've said. for the upper triangular matrix. So for the lower triangular matrix, so this one, let's just do the example. So we have, so this my diagonal, so let's have diagonal of 1. So for the upper one, we said the members that are above it are non-zero. For the lower one, the members that are below it are non-zero. So let's say this is 4, so let's say this is 5, let's say this is 6, right? The ones that are above the diagonals are 0. So this is the lower triangular matrix. So this type of special matrices are actually very useful. So when you're solving questions or in the application of matrices. So for the 11th type of matrix that we have, 11th type of matrix, so the transpose of a matrix, transpose of a matrix. So what does transpose of a matrix mean? So transpose of a matrix is simply interchanging the rows of the matrix with its column. So let's say we have a matrix A, and then we say the matrix A has 1, 2, 3. Let's write this properly. 3 and 4. The members of matrix A is 1, 2, 3, and 4. Then the members of A transpose will simply be, so we're interchanging the rows with its column. So this row, the members of this row are 1, 2 of the first row rather. The members of the first row will now be interchanged to the members of the first column. So in such a way that have 1, 2. And the members of the second row will be interchanged to the members of the second column. So 3 and 4. And this is our transpose. So when you're transposing a matrix, we're simply interchanging its rows and columns together. So for the 12th matrix or 12th type of matrix that we have the symmetric matrix. Okay, so for a symmetric matrix, for a matrix to be symmetric, we're simply saying after we've transposed the matrix, it will be equal to itself. After we've transposed the matrix, it will be equal to itself. So let me try and clear this area so we have more space to work with or work in. So remember, we said for a matrix to be symmetric, it means that, okay, so we said number 12. So for a matrix to be symmetric, okay, let's just write the symmetric. Okay, so for a matrix to be symmetric, it must mean the matrix itself is equal to its transpose. So when you transpose the matrix, it's actually equal to itself. So let's say we have a matrix A, and then A, the members of A or the elements of A are 1, 2, 3, 2, 4, 5, 3, 5, 6. Okay, so let's say whether this matrix is symmetric or not. So let's try and interchange. So A transpose would be equal to, so just transpose this matrix. So remember what we said when I transpose it. The first row becomes the first column. So the first row, 1, 2, 3. I'm writing this first row. I'm writing it as a column. The second one, 2, 4, 5. So write as a column 2, 4, and 5. And lastly, 3, 5, and 6. So you can say, so if these two matrices are equal, if A is equal to A transpose, you can say the members of the first row 1, 2, 3, 1, 2, 3, 2, 4, 5, 2, 4, 5, 3, 5, 6, 3, 5, 6. Then we say this matrix A is symmetric. So it's like a mirror, the elements are mirroring each other. That, no matter how you twist and turn, you always arrive at the same unique identifier with the of all the elements that are inside of the matrix. Okay, so the 13th type of matrix we want to talk about will be the skew symmetric matrix. So let me just clear this. Skew symmetric matrix. Skew symmetric matrix. Now, what does it mean? Skew symmetric. Skew symmetric. Okay. Now, would say a matrix A would be called skew symmetric if A transpose is equal to the negative or the negation of the matrix itself. That is, after transposing your matrix A, you find out that the transpose is actually equal to the negative of the initial matrix itself. So without wasting, let's just take an example. So let's say we have A equal to 0, 2, minus 3, minus 2, 0, 4, 3, minus 4, and 0. So now, remember, for it to be skew symmetric, A transpose must be equal to negative A. So let's find out negative A. For negative A, it just means I'm multiplying this matrix by negative 1. Of course, we've not done multiplication of matrix, but this is quite easy because this is a scalar multiplication of matrix. So let me try and multiply A times minus 1. So this just means minus 1, multiplying all the members. So 0, 2, minus 3, minus 2, 0, 4, 3, minus 4, and 0. So okay, so let's just do that again. Okay, so now I'm going to be using this negative 1 to multiply all the elements inside of this one after the other. So minus 1 times 0, that gives me 0. Negative 1 times 2, that's minus 2. Negative 1 times minus 3, so that's 3. Negative 1 times minus 2, so that's 2. Negative 1 times 0. Negative 1 times, so that's negative 4. Negative 1 times 3, so that's negative 3. Negative 1 times negative 4, so that's 4. Negative 1 times 0, so that's 0. So this is my negative A, so matrix A. Now let's now transpose this matrix A and see whether the transpose of A will be equal to the negation of A. So transpose of A transpose will simply be, so interchange the rows and columns. So here I have 0, 2, minus 3. So here I have negative 2, 0, 4. And I have minus 3, negative 4, and 0. So you can say A transpose is not equal to A, so hence the matrix is not symmetric. But is this skew symmetric? You can see A transpose and negative A, 0 minus 2, 3, 0 minus 2, 3, 2, 0 minus 4, 2, 0 minus 4, minus 3, 4, 0, minus 3, 4, and 0. So you can see that this matrix, or we can say rather, that this matrix is actually said to be skew symmetric. All right, so this is all we have for this video underneath types of matrices. In our next video, we'll look at how to add matrices and subtract matrices from each other. So I hope the concept or the types of matrices is quite clear. Remember, we're going to be meeting all these different types of matrices, whether we're adding, whether we're multiplying, whether we're finding determinants, whether we're trying to look at how to solve systems of simultaneous linear equations. So these types of matrices are actually very, very important. So if this video has been helpful, so you can just drop a like, a comment. You can also share to your friends, your colleagues, your siblings that are preparing for exams or taking exams in maths, in further maths, in physics also. So because we use the concept of physics, even in for those that are undergoing courses like maybe computer science and so on and so forth. So do well to share to them. So thank you and bye bye.